Okay, shall we start? Okay. Assalamualaikum and good morning to those in Malaysia, and hi everyone. So dear respected professors and fellow academicians, firstly I would like to say thanks for joining me today. So I'm Ashrani from the Department of Electrical, Electronic and System Engineering, Faculty of Engineering and Build Sciences, Build Environment, Universiti Kebangsaan Malaysia or UKM. And I will be the moderator for today. So we will hopefully have an interesting forum today with our two distinguished speakers. This forum today is made possible with the support of various parties within UKM and collaborators outside. I think without further ado, I would like to invite Associate Professor Dr. Zawiah, who is the Deputy Director at IDEA-UKM, to give a few opening remarks. Okay, floor is yours, Dr. Zawiah.
Thank you, Dr. Ashrani. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good morning to everyone. I'm not sure at Dr. Micheal King and Dr. Rhodri Smith, is it like 8 and 9 p.m. at the moment? I believe both of you at US. So it should be like 12 hours, right? Okay. It is both a privilege and a great honor to welcome all of you to today's international webinar entitled Medical Imaging Research 2025 in the Age of Advanced AI. This event is proudly organized by the Center of Integrated Engineering System and Advanced Technology, INTEGRA, as mentioned by Dr. Ashrani just now. This is under the Digital and Technology Transformation Research Cluster of IDEA-UKM. And at IDEA, we are entitled with the Research and Innovation Strategic Planning and Execution at Universiti Kebangsaan Malaysia. And we are proud to have the Digital and Transformation Research Cluster as one of the most active research cluster in UKM. This webinar is also made possible through the valued collaboration of the Faculty of Engineering and Built Environment, FKAB. Thank you very much to FKAB, as well as the strong support of our co-organizing partners, the Malaysian Nuclear Agency, and the IEEE Kuala Lumpur section, and also I think MEAP, if I'm not mistaken, I saw the logo there. And with regards to the webinar title, as we advance into the future of healthcare and engineering, we are witnessing a profound convergence between medical imaging and artificial intelligence. From diagnostic radiology to predictive analytics, AI is rapidly redefining how clinicians and researchers addresses disease detection, clinical decision-making, and patient management. We are undoubtedly entering a new era. One is data-driven, technology-empowered, and rich with transformative potential. Today, we are honored to host two esteemed speakers who are pioneers in their respective field. And from the information that I obtained, we have Professor Dr. Micheal King from the Department of Radiology, Chan Medical School, University of Massachusetts, USA, a leading voice in the integration of advanced technologies in radiological sciences. And also with us, we have Associate Professor Dr. Rhodri Smith from Alberta Health Services, University of Alberta, Canada, who is an authority in healthcare analytics and medical imaging research with deep insight into the application of AI in clinical environments. Okay. We are equally pleased to welcome also our session moderator, Dr. Ashrani from FKAB-UKM, whose interdisciplinary expertise bridges engineering and medical innovation. Thank you, Dr. Ashrani, for being the moderator for today's session. A bit about the IDEA. At IDEA-UKM, our vision is to drive excellence in research through strategic clusters that align with national and global goals. And this webinar represents a clear embodiment of that mission. promoting interdisciplinary collaboration, championing digital innovation, and supporting Malaysia's aspiration to become a knowledge-driven, high-technology nation. To all participants, academicians, researchers, students, and innovators, we thank you for being with us today. We hope that this session will inspire meaningful dialogue, foster new collaboration, and stimulate impactful research in the ever-evolving landscape of AI in medicine. Before we proceed, I would like to express my sincere appreciation to all organizing and technical committee members, as well as our supporting partners and volunteers for their tireless efforts in making this event a success. And with that, I hereby officiate the opening of the webinar, Medical Imaging Research 2025 in the Age of Advanced AI. And may this morning be filled with insights, knowledge sharing, and fruitful exchanges. Thank you. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh. I pass the event back to Dr. Ashrani.
Okay, thank you again, Dr. Zawiah, for your kind remarks, introduction, and support of this event. Okay, so since I believe in our audience we have both clinicians and researchers such as myself and the speakers, I want to set the mood a bit before we go into the very technical details that we will talk about. So what do we mean by AI now in the middle of 2025? So we are mid-year already. So for those with the technical know-how, I think you may equate it with deep learning. Okay? So what is the capability of deep learning currently? For the end user and general public, I'm sure you are familiar with ChatGPT and other similar chatbots. And I think a few months ago, everyone was trying to image generation. Am I correct? So if you notice my background here, does it look like a generated image or a real image? Actually, I wanted this to be part of the poster, but it's a bit too artificial, maybe. So this is actually the image. This is not actually, I'm not taking the task of the speakers. This is just setting the mood, okay? So this is obviously artificial, okay? So what about if I show this image, which might be more relevant for today's forum? So maybe the clinicians can tell me which ones are artificial or not. So actually everything in the left of the screen is artificial, everything on the right is actual image. So I think enough of that. Okay. Yeah. So I think maybe some of you have also tried this with ChatGPT and other chatbots. So actually, since I have a little bit of sore throat, I have a co-host today, which is not human. Still loading up. Hello, ChatGPT. We have an interesting forum this morning with two distinguished speakers. What do you think about it?
Hello, that sounds exciting. Forums with distinguished speakers are a great opportunity to learn and discuss important topics. What's the main theme of the forum today?
Actually, I want you to be my co-host. Is that okay?
Of course, I'd be happy to help as your co-host.
Okay, wait, that's enough. So I want to try something else. So you might want to try that it by yourself. Okay. Since I said I have a co-host, let's see if he can introduce the speakers. Hi again. Can you introduce the speakers for us today? It's loading.
Sure. Here's how I'd say it in English. Good morning, everyone. It's my pleasure to introduce our two distinguished speakers for today's forum. Our first speaker is Professor Dr. Micheal King, a leading expert in nuclear medicine imaging. He holds degrees in physics, radiation biology, and biophysics, and has served in top academic roles at the University of Massachusetts since the late 70s. He's published over 200 peer-reviewed papers, chaired major international conferences, and received numerous prestigious awards for his contributions to medical imaging science. Our second speaker is Associate Professor Dr. Rhodri Smith. He trained in physics and medical imaging in the UK and has held key positions in both research and clinical nuclear medicine across the UK and Canada. He's currently a provincial nuclear medicine physicist with Alberta Health Services and an associate professor at the University of Alberta, with research focusing on nuclear medicine imaging. We're honored to have them both with us today. Would you?
Okay. So there's one final test. That's for maybe going to really technical stuff. Okay. It's loading again. This is the thing about technology. Can you ask the first speaker the first question? It's not working. Okay, anyway, I think that's enough for ChatGPT. So I would like to ask Prof. Micheal King, can you give basically an overview of how things have changed in your research area since you first joined UMass past 45 years? Okay, so the floor is yours.
Okay, thank you very much for setting up my topic for the first talk. I want to apologize to everybody. Not only is it late here, but I've picked up a cold, and so my voice is a little bit different than it normally would be. And every now and then I'm going to pause to cough, it seems like. So I apologize in advance. But let's start by getting my slides up and make sure I pick the right one to begin with. Yeah. Yeah, that's the one. Okay, so we'll share this and get it up to full screen. Let's try it again. There we go. Okay, I'd like to thank Dr. Ashrani for inviting me to give this talk. I've known him for quite some time, and Dr. Smith also. So it was a great pleasure to be able to talk with him on this presentation today. And I'm going to be talking about medical research and nuclear medicine imaging, a 45-year perspective, which is about the amount of time I've been at UMass. So that's a number has some correlation with my history at UMass. And I want to kind of give an idea of how things have changed over the 45 years, heading towards us getting into having AI now being a very important part of our research going forward. So I'm going to introduce what nuclear medicine imaging is, kind of follow one research topic's progression over that period of time, because it's hard to follow everything for all different modalities. So I'm going to stick with one modality and one topic, so I can do a pretty good job on that one. And then you can see how we went from, basically playing with tinker toys and things like that to getting into doing some really serious image processing and stuff as the time went on. And the topic that I'll be talking about is a correction of attenuation. And again, I'll take it from the very beginnings of SPECT, single photon emission computed tomography, which is the modality I'll talk about, up through today with AI, but the AI will be in the next talk. Okay, so what is nuclear medicine, and nuclear medicine is a way of assessing the physiology and pathophysiological function in patients by using something akin to what people would do if they wanted to trace a flock of birds. They were an environmental scientist and they wanted to trace a flock of birds. They would capture some of the birds and put radio transmitters on them, then release them with the flock again. And hopefully the flock would not run away from them so that they would accept them back in so that these birds could, track how the migration of their whole flock went. Well, instead of using birds, we're trying to do patients. And so what we do is we put in something which emits a high energy photon and can make it out of the patient's body. So we give this to the patient by either injection or having them eat it, or in some cases breathe it in. So we have this radioactive material that they're going to breathe in. And the material emits this radiation that can penetrate the patient's body. It has to be high enough in energy to do that. So it's typically either an X-ray or a gamma ray. If it's an X-ray, it might be, for example, coming out of thallium-201. This is the radionuclide that emits about 70 keV characteristic X-rays. And they're emitted, thallium undergoes electron capture, which means that one of the shell electrons gets too close to the nucleus and a proton gobbles it up to become a neutron. So we lose one positive charge in the nucleus itself, and we get off an electron that comes out of this. Actually, we get off just a photon. There's no charged particles coming off because the electron was taken out of a shell. It's a missing place there, so another electron drops down to fill that vacancy. So we can get off an X-ray, or we can get out a gamma ray. So in this case, we have some nucleon or proton inside the nucleus that's in excited state. And there's a lower energy state available for it to go to, so it can become even more tightly bound. So it does so. When it does so, it has to emit some energy, and we call that energy a photon. An example of that might be the radionuclide technetium-99M. M stands for metastable. So this is something that has a finite half-life, but is destined to change. And it's going to change to getting to the ground state. So this is an excited state. Something's up higher than it should be in the energy levels. When it comes down, it goes from being the excited state towards the ground state. It may not go all in one leap just to the ground state. It might take several, but eventually it'll get to the ground state. But anyways, if it lasts for a finite period of time, it's called a metastable state. And technetium-99M is probably the most widely used radionuclide in nuclear medicine. Another way we can get out these high energy gamma rays is to have the radionuclide emit a positron. So we have something, if you're proton rich, turns out that's not favorable for being a nuclide because those protons have the Coulomb repulsion as well as the strong force that holds the nucleons together. So the the protons inside the nucleus of very large radionuclides, and some smaller ones, will try and rearrange to make their proton to neutron ratio better. And they will do that by emitting a positive electron. So the proton changes into a neutron by the emission of a positive charge. And the positron is the antiparticle to the regular everyday electron. So it comes off, loses the energy that it was given in emission, comes to rest. And when it comes to rest, since it's an antiparticle, it'll couple up with a electron that's already there. The two will form positronium for an instant and then annihilate. And we get off two 511 keV photons. The rest mass energy equivalent for an electron is 500 keV. We have a positron and an electron annihilate, so we get twice that amount of energy produced. To conserve momentum, they go off in opposite directions. And an example of that might be fluorine-18. So we have the radionuclides, and then we put them on some pharmaceutical. This is the bird. These are the radio transmitters. This is the bird that we're talking about. And we would pick some chemical form of it. So for example, for thallium, it's really easy. We just use thallium chloride. It's a salt. It emulates table salt, sodium chloride. You put that in, it freely diffuses through capillary beds. So it will leak out of the first capillary bed that it gets to. So it's a good thing for tracking blood flow. We do this for looking at the blood flow to the heart. Once it gets out of the bloodstream, there's a potassium sodium pump. Thallium acts a bit like potassium, so it's pulled into the cells and held in the cells. And we get an idea what the perfusion is to the walls of the heart, for example, for doing cardiac perfusion imaging. Or we could use Tech 99M, and we'd label it to methylene diphosphate, MDP. MDP is something that latches onto the surface of bones. So anytime you got some calcium exposed in the bone surface, it's going to lash onto there. So this thing would be very good for imaging the bones of the body. I'll show an example of this very soon. And then we have our fluorine 18. And what we do is we take an oxygen off of glucose, and fluorine can go on in place of it. So if you a fluorine 18 deoxyglucose, the oxygen's missing, fluorine goes in place of it. This is in terms of glucose. Glucose is sugar. Cells that are metabolically active suck in the glucose, just like, kids love to get candy bars. Well, the tumors, for example, that are rapidly dividing want to pull in a lot of energy, so they're going to be pulling in the glucose here. And now we've got a great agent for imaging tumors, for example. And this is FDG, or fluorinated deoxyglucose. Well, once we have this radio transmitter and it's put onto the bird and turned into the flock, or the radionuclide is combined with a pharmaceutical to form a radiopharmaceutical, and then put into the body of the patient, we have to make images. And we call our device for doing that a gamma camera, even though it does image X-rays, because X-rays and gamma rays are the same thing. They just come from a different site of origin. So we have these gamma cameras looking a little bit like what I have over here to the side. And this is to represent, and this is a physicist's view of the patient. Here we have the heart, the left ventricular wall, full of thallium, for example. So we're going to be imaging that. The photons are going off in all sorts of different directions. And we have to take these photons and turn them into an image that we can put onto our detector. The detector is the crystal behind the collimator. So the first thing that happens is these photons come off. The ones that come into an angle to the collimator strike the walls, and they're preferentially absorbed. Not everyone may be absorbed, but the vast majority are. So they're absorbed in these little lead septa that come down through here, whereas the ones that make it up between the septa can actually gain access to the crystal. So we have this thing acting like the lens of a camera. But instead of focusing the photons on the detector, it does it by absorptive collimation. It throws away all the ones that are going in the wrong direction. So our sensitivity gets knocked down by a factor of 1,000 or so, compared to what it would be if we let all of them through. But we have to do that in order to get an image, and I'll show you an example of that in a moment. So we have the crystal. The photons come in, interact in the crystal. They're absorbed. When they're absorbed, this crystal preferentially takes part of that energy and turns it into light. The light goes off in all directions. If a flash of light occurred right here in the center, for example, some light would go to the first PM tube, some to the next, and some to the other one. Same thing this way. And the light would be, this one would get the most. These two would get less, exactly the same amount, but less if it was right in the center. Same thing for out here. And we can take that pattern of the light being absorbed at the different photomultiplier tubes, run them through preamps, and bring them into some position determining circuitry, or bring them into our computer and do this digitally. And we can take this pattern and turn it into the location in the X direction in the crystal where the flash occurred, the location in the Y direction that's coming in and out of your of the monitor here, and then an unblank signal, which is just the total amount of light that came out, an index of that, and that's the energy of the gamma ray. And that's important because we have scattering taking place in the patient too. Photons can come out, scattering come in, and scattering, they lose energy. We don't want to image these scattered photons. So we take the energy that's deposited and say, I want to image, only want to get all of the energy deposited. I don't want to get the ones that lose some of it. because they're scattered photons. So we use this to select the photons that probably have not been scattered. And this goes into forming our image, which is then sent out to the computer. Okay, our process looks something like this. This is a picture of a gamma camera with a small amount of technetium-99m put into a little droplet and a capillary tube stuck in front of the camera, about 10 centimeters in front of the face. Excuse me. And there's no collimator. So all we do is we get the idea that there is some point causing it. And if we take the distance from the point source to the crystal, it's 10 centimeters to the face if you're right below. You go out to the edge now, it's the hypotenuse of some triangle looking like this. And that hypotenuse is a lot longer than this one. And the intensity falls off as the inverse square of the distance just by using the standard, dispersion of photons coming out of a point fluoride. So our only index of energy resolution is just the inverse square law. But we get great sensitivity. We're now getting about, that's about 7.2 million counts, the maximum being about 1,400. But what we do when we put the collimator on there is, well, we throw away most of those counts. And now we're only getting about 18,000 counts. But the maximum at the center of this point is just about the same as that. And that tells us that, yeah, okay, so what we've done is we've thrown away a lot of these counts to get that image. And so with the collimator in place, we can now take pictures of people and get things that look like this. This would be if we have a person who is an MDP in them, the bone imaging agent. It localizes on bone surfaces. This is somebody who's young because they have their growth plates highlighting, and there's a lot of bone growth going on in both bone plates, so you have those lit up. There's also a little bit of extra here. So this is where the pathology that they were looking for probably is occurring. But notice we have this view looking like this. That's like looking at the front of the guy. You can see his mouth and nose area, see the ribs. Backbones kind of fade because that's further back in the body. So what happens is that photons coming out towards the front are detected by one camera head. That's going to be called the anterior view. And in that, we're able to resolve things, but we don't see things from the back quite as well because they're all attenuated and resolution falls off with distance. So this image is great for the front, but not so good for the back. Well, we want to see what's going on in the back of the patient too. So we have another camera down there, and now we're picking up this activity in the kidneys. Here's the backbone, the spine, and again, the growth plates. And again, there's something going on in this region. Okay, so what we're noticing is that there's a difference between the two of these because of attenuation. So we really need to worry about attenuation, and we should be correcting for it if we want to, be able to see all sides or information from all depths. Okay, so instead of doing planar imaging like that, we'd like to do tomography. We'd like to go to emission tomography, go to 3D. And there's two different flavors we can do in nuclear medicine. One is called single photon emission computed tomography, or SPECT. And SPECT employs a collimator, that thing we just talked about, that throws away a lot of photons to get the image. And that collimator defines the path which photons can originate in the object and make their way into the body. And that's how we kind of figure out where the material was in front. But notice photons come from all depths. So all depths are stacked together in that image. There's a preferential for the ones that are shallow because of attenuation, but they're from all depths stacked together. Okay. The other one is to go to our friend, the positrons emitters. And so we get positron emission tomography, or PET. And in PET, since we get two photons coming off in all directions, we put a ring of detectors around the patient. We get two detectors that say, aha, I got a 511 kV photon. And we match them up time-wise and say, they're in coincidence. So now we can take and draw a line between those two detectors. And that tells us that the annihilation took place someplace along here, and the site of emission wasn't very far from the site of annihilation. So we can do that in positron emission imaging. To go back to SPECT, again, we would be using a gamma camera for this. It would be rotating around the patient. Here's one of them. We'd have the collimator, and that'd be kind of like the blinders on a horse. You would put the things up like this, and the horse is only looking straight in front. They're not worried about what's happening at the side. Well, we're throwing away the things to either side here. Although we don't perfectly hold it down like this, it turns out that the resolution actually spreads out a bit as you move away from the face of the collimator. And if we were to sit at this angle, we would wind up acquiring counts as they went across. They become from all depths. You might get an image like this. So it's a function of angle and distance across the detector, and this would be our projection that we'd get. And if we then took that camera and rotated it around the patient, let's say here's the activity of the patient, we'd wind up getting a projection image that looks like this. And this is called a sinogram because things in here trace out a sine wave. Every point here has a different sine wave pattern in the sinogram. We use that to decode these because when we want to go back to figuring out something like this from the sinogram data, we use the idea that each point here wiggles a bit differently in our decoding it or in our reconstruction algorithms. Okay. Well, in reality, we said there's actually attenuation taking place. So some of the photons heading this way get stopped. There's actually some photons are going to go that way are scattered and they don't get collected, but other things might be scattered and get collected over here that we didn't intend to. So that gives us some counts back. The counts that come back are this is ones we don't want because they were scattered, and this is diminished from the original value by attenuation. Okay, and what does that look like? It looks like this. So now we do the same thing, but as we're collecting the data, we're accounting for attenuation and the blurring of resolution. And you can see that top of the spleen right here kind of fades away and then comes back in and then gets bright again as we get around close to it over on this side. So these things fall into the sinogram. Okay, well, when I go on and reconstruct it, this is the starting image. If we do filtered back projection and we took the first set of data, the data that wasn't messed up by attenuation or anything, that's the beginning. Get a nice looking image. There's some angular aliasing going on here because I should have sampled around the patient a bit more finely than I did. But other than that, it's a very nice looking image portraying what was going on over here. But when you throw in attenuation, first thing you notice that the patient seems to have some dermatological disease. The skin is hot, so you better send them out to a dermatologist. But that's because of the attenuation. So that we have a bias. The things that don't have to go very far to get out tends to get out easier than the ones that have to cross the patient and go a long way. So we wind up getting, it dips towards the center. And also we get some fuzzing in here. Originally the heart should have uniform activity in it, but now we're getting the apex very bright and the different walls of the heart are now at a different intensities when they should be the same. Well, we should probably try and correct for that when we do our reconstructions. And that's the project we're going to talk about. How do we correct for attenuation? Well, what is attenuation? Well, if you have some original intensity that's emitted, photons heading in a direction and they go through some material, they're not going to all make it out. Some will be either absorbed or deflected to go off in a different direction. That's the attenuation, so that what comes out is less than what went in. So what comes out is what went in times e to the minus, and this is a sum of all the different types of materials it passed through and the thickness of each one of those. So if it's all the same material, this would be just a single mu, and this would add up to being just the sum of the distances. If it was different materials, you'd have, part of it might be a soft tissue, some air, and then some bone, and then some more soft tissue, so on and so forth. That's what this represents. Okay, and the mu in here, the mu is the linear attenuation coefficient. It's the probability of attenuation per unit distance for a very small distance based upon that. And what it depends upon is the energy of the photon. So if I have a low energy photon, it's going to be attenuated more rapidly. Its mu is going to be larger. So a plot of an exponential function put on semi-log plot. So this is a log. This is regular. This is depth in the patient. And the thalliums are going to be, since they're about 70 keV, will be attenuated more rapidly than the technetiums, which are about 140 keV. And they're going to be attenuated more rapidly than the I-131s, which are 364 keV. And the 511s from annihilations, they'll be attenuated at least, but in reality, they are the most in need of attenuation correction. And that's an interesting thing for you to look up someday as to why that is. Okay, so they depend upon the energy, the density of the material. The higher the density, the more atoms they're going to bump into. And the atomic number. Generally, the higher the atomic number, the more they're going to be attenuated. Okay, so how did we figure out maps of those attenuation values in mu? Well, when we first started out, we were very clever, but we didn't have a lot of technological abilities to do things. So what did we have? Well, we had lots of syringes laying around. So you take a syringe, put a little bit of activity in 2 syringes, and you put them on each side of the patient, bring the cameras over the top, and you'd say, okay, here's where one of these is, here's the other one. Then you put the camera looking this way along the patient. You tape one to the bottom of the bed and put one on the top of the patient. So now here's 4 points. 4 points can fit in the ellipse. I put in there the attenuation coefficient for water, and that's my attenuation map. Not accurate, not great, but better than nothing. Okay, so well, we then realized that, gee, you can kind of see an outline of the patient from the data that you reconstruct, especially if it's a scatter window, because the scattered photons will go off and interact in the patient, and the more tissue that's there, the more scattering you'll get. And they don't scatter in air, so you'll be able to pick out a good idea just by putting that image up and trying to segment the outside of it. And you might do it for 1 slice at a time, or take a chunk of the slices, put them together. All companies had tools for doing this for you. We took a look at, and a number of other people did this too. We were not the first, and we were not the last, and we were not the best, or probably not the best, but we took a look at doing some types of edge detection operations to get the outside of the patient automatically, and then to try and get the lungs, so we could take and put into here soft tissues where we had the boundary of the patient to what we called the lungs, and then have the lung be the attenuation coefficient for lungs. So we'd have something a bit better than just a solid attenuation map. And this would be a photopeak window image. This would be the scatter. This is a window down a bit further in energy. So these are all scattered photons we're getting in here. And that means they're going to give us a little bit more information about the density mapping. So these values should be lower than these, just on the basis of having lower density, less scattering going on here than where there's more tissue to scatter. And this was a phantom, and this was a patient, and this was used for a while, but it's not really great and robust. So how do we make things better? Well, we went for transmission imaging. What is that? Well, we had to measure the I sub 0. We did that with no patient around, just took our source, put it opposite the camera, wherever we had it positioned. That gave us I sub 0. We then put the source there when the patient was present, and we made a measurement. So now we have I and I sub 0. You take the ratio of I over I sub 0, and that gives you the transmitted fraction. And from that, you could do reconstructions using filtered back projection or iterative reconstruction or something, and you get a poor man's CT, if you would, an attenuation map, and then that can be used as your thing for guiding what the attenuation values are within the patient. There was a lot of ways that came out to do that. You could have a sheet source down here, so this is all uniform activity, and so it's irradiating the back surface of the patient, make its way through here. You compare that to no patient, and you get an idea that, yeah, there's a lot more attenuation in the center of the patient than there was out at the edges. Or if you didn't want to have a sheet source, it was a little bit cheaper to have a bunch of line sources, so they'd add it with a bunch of line sources. Or, well, you know, putting this thing out there, holding it out there, and having it go around the patient, that's a lot of weight to hold either one of these. It's easier to just have a line. So this is one line of activity. So you take that line source and you can scan that across during the measurement. And the idea is you keep track of where it's irradiating, and you say, okay, the counts in here are due to the transmission source, and everything else, that's from the patient. And as this moves across, you take that window and move across with it, so it's matching it in terms of motion. So you can do that, and that's a way of trying to remove some of the crosstalk between your transmission photons and the photons in the patient body. Typically, these would be 2 different energies. So this might be Tech99M at 140, and this could be gadolinium 153 at 100 keV. So you'd have a different energy window for measuring these. Or you could take and, oops, this is supposed to be a converging collimator, so these holes should have been bent. Gosh, I just noticed that. This thing was published even. Okay, but it says it's supposed to be a converging collimator, so you can have a collimator that's focused at that point source. Oh well. And these photons can make it through the collimator. It's no longer a parallel collimator, but it has a collimation. That's another way of doing it, but you lose kind of some of your ability to do the transmission imaging for the whole patient. You could then do put the line source over here, and you could have that asymmetric, and I got that drawn right correct this time, so that you could have the transmission going like this in terms of the source going through those. Or if you wanted to keep the parallel collimator, you could put the line source over here. But if you went for a higher energy radionuclide, one that was high enough in energy that it could penetrate the septa of the collimator, this one could be measured, and you could keep your same parallel collimator on there. And all you'd have to do really on this one is just have a point source, and it could run back and forth into a shutter on the side. A lot more concentrated activity, easier to shield when you don't want to have it irradiate anything. And except for moving the motion, it's just the motion back and forth along the side. Of these,
probably have 5 minutes left.
5 minutes. Okay, we're going to speed up. So of those, the scanning line source was the one that was used the most. We then, of course, went into doing CT imaging, as you see here. And neat thing about CT is that we don't have to worry about those line sources and stuff like that. We have the X-ray tube and a separate separate detector down here. We're not trying to use these. In the past, we used the camera's detectors itself. So let's go forward with this and take a look. Here's a scanning line source on a camera that we had at UMass. And here's a CT source. It's an X-ray source, but it had a fan beam X-ray irradiation. And the line source gave us an attenuation map that looked like this. Well, this is a phantom, this phantom right here. It had a rod in it that we should have been able to see, but we couldn't really tell the difference in attenuation coefficients that well. This is, we're doing the same phantom, but it's sitting on a platform that moves back and forth. So we see it pretty good with the cone beam, but there really is some plastic in here. This is a version of a heart, if you would. And when you go to a true spiral CT, you can see a nice example of that. So different ways of doing it. This one goes a lot slower around because you don't want things whizzing around the patient that are not contained. You can whiz around inside of a gantry of a CT, but if you go quickly around the patient and they decide to itch their nose when it's going by, you could lose an arm that way. So we keep these going a lot slower. So this might take a minute to go around, and these things would be going around in a few seconds. And okay, well, that's how we can measure attenuation maps. How would you use them to do attenuation correction? In the old days, we could take and go out and do the attenuation correction, kind of like we did when we did planar imaging for dosimetry. You'd have opposing views. And the idea is you said, okay, if I got a source here, I would go this far, X sub A, in the anterior direction, and I'd go that far in the posterior direction. And the counts I got from these two things, I could add them up. By adding them, each one of these falls off exponentially. So here's how the counts from one side would fall off and the counts from the other. If I did an arithmetic mean, I get something that had a dip in it. But if I did the geometric mean, you can see that here. You take the two of these, you take these two measurements, you multiply them together. If you multiply exponentials, you kind of add them. That comes up to be just the distance across. And you wind up saying that, oh, gee, now this is kind of like constant sensitivity across. We can do that same thing to do the corrections for spec, take the projections, multiply them together, then take the square root to get back into the same units of measure. And that works. That's a pre-correction. Post-correction would have been Chang's. You take a tub, figure out how your counts fall off relative to that. With that, you can make a correction, which is kind of like the inverse of this. Here's what the correction looks like. And after you get done reconstruction, you can take this and multiply this times that, and you get a correction. Or you can do it in iterative reconstruction itself, where you're doing your projection or back projection operation. Let's say this is a projection. You say, right now, I currently see I believe there's this many counts in this particular voxel. The value of me was this. The voxel was that size. And I take and figure that all these counts are put at the middle point. Then I say, okay, I'm going to go on to the next one. Well, okay, so these guys have been attenuated when I'm making my projection by 1/2 of the distance here. This one I say, well, they have to go all the way through that one. These counts do. Those counts would only go halfway, but that's another sum I'll be making for these counts, how they're attenuated going out. And I go on the next one, and this one gets, so as I go along, this guy gets attenuated more and more as you go out, just like he would in the real world. Net result, you can put that into iterative reconstruction, and you get images that look like this. Here's our attenuation map. And this is filtered back projection.
Can I ask you to summarize it in 1 minute?
1 minute, okay. Attenuation method for filter back projection. This is a male patient. They tend to have extra adipose tissue. So the net result is that we wind up seeing what appears to be some loss down here in the posterior wall of the heart. But when we do correction for attenuation, it comes back. You can see the dip here, dip there. So we're able to correct for the attenuation and the reconstruction for the male. For the female, the opposite takes place. They have breasts. So now it's the anterior wall that seems to be a little bit cool. But when you correct for attenuation, we're able to account for that. And that's the end of my talk. So next time I'll talk more about where artificial intelligence comes into all this.
Okay, thank you, Prof, for your very interesting talk. Maybe some of the audience are not familiar. So basically, this is the history of how nuclear medicine imaging has developed before we go into AI. So I think without further ado, I think I want to call for the second speaker, Associate Professor Rhodri Smith. So the question for you, maybe Prof. Mike can share your slides.
Yeah, I've stopped sharing, so you should be able to.
So for Rhodri, because he's my friend. Can you give the other side of this talk, this forum? So how has AI or computer vision application in medical imaging has developed at the same time as the images themselves has developed? Okay, so what's yours?
Thank you, Ashrani, very much for the introduction. Let me just start the presentation. Great. So thanks, Mike, for setting the tone there with some nuclear medicine background. I thought that was a great talk. So today I am going to talk a little bit more in depth about medical imaging and AI applications.
Sorry, can you try to present full screen? I'm seeing your desktop.
Oh, okay. Sorry. Let me just share.
Just to make the slides good. All right.
That better?
Okay. Good.
Yeah. Okay. Cool.
Okay, please continue.
Yeah. Okay. Sorry. So yeah, I'm going to give an overview of medical image computing. I'm going to go from pre-machine learning era medical image computing right up to advanced medical imaging, AI, and different applications. I'm aware that there's possibly some audience members that haven't got a background in medical imaging or AI, and I do apologize because the learning curve, I would say, is a little steep. But I do try my best to break this down from the fundamental levels and then go up that learning curve. But it is slightly steep. And if anyone has any questions at the end, and even offline want to discuss anything, then feel free to drop me an email as well. So I'm going to talk about, there's a microwave timeline I have there, and it's from pixels, which are the fundamental building blocks of medical images, to then how we can perform operations on pixels to try to get some kind of understanding from a medical image. Then how researchers started to introduce what we call priors into those operations in order to have probably more of a constrained set of rules on how we can extract information from images. Then research advanced and we started to extract more advanced patterns from medical images. And now algorithms have advanced even further, where we have promptable algorithms where we can steer the behavior of particular AI algorithms. I will also touch on some future work around causal reasoning, which is linked in the next talk. So here is a summary of the content. I will just give a very brief overview of medical imaging, and I will include some of the key tasks that we need to consider within medical image computing. I'll also talk about the two main methods of image understanding, which is a top-down approach and a bottom-up approach. Then I'll talk about intelligence. What do we mean by intelligence? I'll introduce 3 macro waves of intelligence, and I'll describe something called the label mountain, which is related to the amount of human effort that is required to implement these algorithms. Then I'll introduce a more granular view of intelligence, and I'll introduce what I've developed here, it's an 8-axis capability metric, which allows us to then compare different algorithms in medical image computing. So then we can start to look at how medical image algorithms have evolved, and we will look at then the microwave timeline, how we went from fundamental pixel operations to prior information, to patterns, to prompts, to causal reasoning, hopefully. I think that might form part of the discussion at the end. And I'll compare algorithms at each individual wave head-to-head. So medical imaging, there's lots of imaging modalities. Mike has described very well nuclear medicine imaging. And that is the field that both myself and Mike specialize in. But there are lots of different imaging modalities within medical imaging. And even the 3 I have listed here, they are the main players in what you might call radiology, but there's still lots of other imaging modalities I haven't included. But usually within medical imaging, the physical process that's used to acquire the image actually gives you a direct indication of what the imaging modality is called. MRI, for example, uses magnets, and we can use magnets to perturb proton alignment in tissues. We can then start to look at the different responses of protons to external magnetic fields. And MRI gives us great soft tissue contrast because proton density is very much subtly different in different tissue types. We then have CT, which uses X-rays, and we can probe tissue density. So we're looking at how X-rays are attenuated through the human body. And then we have nuclear medicine, which Mike spoke about, where we can actually look at physiological function using a radiopharmaceutical. And that radiopharmaceutical will bind itself to a physiological process, and we will then have gamma rays or X-rays emitted from that radiopharmaceutical so we can image function. So we have some examples here of medical images. So these are 3D images, and we're taking 2D slices through the image. And we can see this is a CT example, and we can see that the lungs are black and the bones are white, because in CT imaging, we're looking at tissue density. Then we have an MRI image, and we're looking at soft tissue contrast, and we can start to see in great detail things that are going on in individual organs. So I think it comes into view here. We can see great detail, for example, in the kidney. This isn't possible on CT. And then we have a nuclear medicine image. This is a PET image, and we're looking at glucose metabolism, which is more avid in cancer cells. And we can start to see greater increased uptake due to this glycolysis in cancer cells. So nuclear medicine imaging is great for cancer detection, amongst other things. But all these imaging modalities give us different clinical information. I'm not going to go into details on that clinical information, but we want to try to develop algorithms to assist in our understanding of these medical images. I think that segues quite nicely into the next slide. So as medical imaging researchers and computer scientists, we're looking at some fundamental tasks that we like to perform within medical image computing. We want to improve diagnosis. We want to quantify accurately disease processes, and we want to be able to personalize therapy or treatment. So these are the 3 aims that we like to aim for in medical image computing. So how can we go about doing that? So this slide looks a little bit busy, but I think that it's broken down quite nicely, the key tasks and how we can reach those aims. First and foremost is processing and enhancement. Image processing and image enhancement. We want to remove noise from an image, remove degradation from an image, and this will actually allow us to clean up the image for further downstream tasks. Related to processing is denoising and deblurring. For example, if a patient is moving within a scanner, it might cause a motion blur, or if the scanner itself actually creates some kind of artifact, due to the different methods of sampling the signal, we get a blurring artifact. So we want to clean up the image, and we want to denoise and de-blur the image to increase quantitative accuracy. We also want to extract biologically meaningful features. There's a whole host of different features that we can extract. And these features then, again, feed onto other tasks. And one of those main tasks are segmentation and classification. We want to be able to look at an image and be able to classify if it's diseased or not, if it's normal, if it is got a problem or pathology, what scale or grade of that pathology has it got. And also segmentation. We want to be able to group pixels within an image into certain types. Group all pixels that are part of the myocardium or part of a tumor that we've identified. And we do all this in order to identify anomalies. I've mentioned registration. I've mentioned motion before, but registration is also a key part of how we can improve diagnosis and quantify disease. There's a multiple reasons why we want to do image registration. It might be as simple as aligning two images from two different imaging modalities. It might be that we want to register images to a certain phase of a respiratory cycle to remove motion blur. It might be that we want to track how the heart is beating. So we need to be able to track the motion in order to quantify the ability of the heart to actually beat and contract. We also might want to monitor disease progression. So we might want to see how a patient is from a longitudinal point of view. Is their tumor shrinking? And we can use registration for all those things. And ultimately, we want to be able to interpret the image, and we want to assist the clinician in doing that. But now we can even build algorithms that aim to automate a lot of these processes. With modern algorithms, now we can even, they're actually very data hungry. So there's algorithms that can synthesize data. So we can synthesize data where we have class imbalances. So for example, if we have, we find it particularly difficult to get data with samples from a rare disease, we can synthesize data or augment data in order to feed these data hungry algorithms. And then finally, multimodal reasoning is when we want to actually fuse information from different data sources in order to try to build a knowledge base for improving the ability of a clinician to diagnose, predict, and treat disease. So we've talked about medical imaging, and I've touched on image understanding in the contents there. But there's two fundamental ways we can start to understand an image, and that is from a top-down approach, which is when we have high-level knowledge, heuristics or rules, and we want to use those rules in order to guide how our algorithm is actually interacting with the image and giving us information from that image. So that's the top-down approach, and we have the bottom-up approach where we actually extract patterns from the image in order to try to learn patterns that are perhaps correlated with certain things like disease processes. So there's multiple different algorithms that we can use for top-down and bottom-up processing. Just some very brief examples here. For top-down, we would have a physics model of how we think a tracer is moving in the human body. Or we would have a simple thresholding algorithm and say pixels below a certain level are noise, let's get rid of them. Or we might have an atlas that we want to register our image to and see how far away we are from that atlas to quantify the diseased state. So the top-down approach is when we have heuristics and rules and a priori knowledge that we are imparting on the process of trying to understand the medical image. The bottom-up approach is when we're actually learning patterns from the data. So we're learning filter responses, for example, or we're learning how certain pixels might cluster together in certain relationships. There's two eminent researchers who have looked at image understanding, and I've listed them both here, actually. So we have David Ma in 1982, who came up with his theory of vision. And he eloquently said that vision is about knowing what is where by looking. So fundamentally, for image understanding, he was concerned with identifying what we are looking at and then spatially locating what it is. Tommaso Poggio, who worked with David Marr, then said in a bit more detail that any practical machine vision system will need both bottom-up and top-down processing in order for us to have a full understanding of an image. And when we have a full understanding of an image, can we start to actually build algorithms that can extract information and then laterally on reason about an image type and possibly things like prognosis. So before we talk about different imaging algorithms, let's just touch on intelligence and the evolution of intelligence. So the USA's Defense for Advanced Research Projects Agency, or DARPA, their main concern is actually the evolution and the advancement of artificial intelligence. And they've split up intelligence into 3 waves, which describes how intelligent a certain algorithm might be valued. So wave 1 is very much symbolic or handcrafted rules. So some of the early heuristic approaches that I previously mentioned would fit into wave 1. Wave 2 is when we have statistical machine learning, where we start to learn patterns from data. And wave 3 is when we start to have algorithms that are actually contextually aware. They've also got the ability to adapt, generalize, and they should also have explainability and transparency. There's some contention between if some modern algorithms are currently wave 3, perhaps that can form part of the discussion. But these are the 3 waves described by DARPA, and we have the label mountain there. The label mountain is how much labeling effort is required to implement these algorithms. Granted, the handcrafted algorithms required very little labeling, but it did require a lot of a priori expert knowledge. The wave 2 algorithms, we started to learn from data, so we started to need labeled data sets. And then we reached a fully supervised peak where we require hundreds or thousands of labeled data sets in order to extract patterns from images in order to understand the image. And we're very much there at the peak of purely bottom-up processing. Wave 3 then is when we start to build algorithms that can label data themselves, semi-supervised and self-supervised algorithms. And then when we get right down the bottom of zero-shot learning, this is when we have an algorithm that requires very little labeling and can provide output for generalist tasks for different imaging domains. Just to point out here, though, on wave 3, I'm not trying to say that the advanced algorithms require less data or less amount of effort. Millions of examples have been used to construct these algorithms, but it's purely from a human interaction point of view to utilize these algorithms that have got that baked-in knowledge. So how do we get here? So the evolution of paradigms in medical image analysis is what I will speak about next. So from the 60s and 70s, we very much had that top-down heuristic filtering processing, where we just had simple rules like thresholding, where we had data agnostic decisions. Then in the 80s, we started to look at more blob detection type algorithms and regional analysis. So algorithms began to kind of reason beyond individual pixels and started to use things like shape and intensity distributions. Then we had more structural aware algorithms, where we started to look at the statistics of populations, and we started to also have anatomical priors and smoothness constraints built into the algorithms. Then in the 2000s was the early feature engineering and shallow learning era, where we would have handcrafted features that we extract from the image and couple those with machine learning algorithms that can learn predictions and predict outcome, or can predict clustering levels of pixels. Then we had the deep learning breakthrough, where we very much went from handcrafted features to features that we actually learn ourselves from the data. And this is what requires lots of labeled data. So the model learns hierarchical features directly from the images. And the famous convolutional neural network is something that excels at segmentation and classification because of some of the inductive bias built into the CNN. It's got it captures a local receptive field and looks at connectivity within that receptive field. And there's something called translational equivariance, where filters will actually respond in the same manner, irrespective of where we are in the image. We then started to have adaptive and generative models where we can actually model the image across a distribution, and we can start to synthesize images. So then we can start to look at synthesizing images with different class imbalances. Then we had the rise of the foundation models, where we had the transformer technology come into play, and we have something called self-attention, where, and I'll explain this in the next presentation, where we start to look at context of the image rather than just locality information. And then we move towards generalist medical AI, where we have large vision models that can respond to prompts, adapt to different context, and even the implementation of things like visual question answering systems, where the user can actually interact with an image, for example, to try to extract some kind of causal reasoning. So here's a list of the actual models that were used during each era. I won't list every single one. You might pick up on some that you're aware of, but just to cherry pick a few, the 1960s was just simple global thresholding. Then, for example, we would have things like Laplacian of Gaussians for edge detection, or the canny edge detector for edge detection. Structure-aware processing, famous models like the active shape model, or atlas-based segmentations. The feature engineering phase was when we started to have these handcrafted features like gradients and histograms of gradients and things like SIFT that would look at different properties of blobs in order to detect corners and certain interesting structures within an image. And then there's convolutional neural networks with the deep learning breakthrough, and the generative adversarial networks with the generative models, and then the vision transformer and the rise of the foundation models, until we come to the promptable generalist medical AI, where we have systems like medical visual question answer systems. And this table here summarizes the different macro waves that we went through of DARPA. In the 1960s, 70s, 80s, and 90s, we were very much in wave one, perhaps early wave two in the 1990s, when we started to use statistical machine learning and shallow learning. And then in the 2000s, when we started to have deep learning, 2010, we're very much at the peak of wave two there with statistical machine learning. And then we start to have attention mechanisms incorporated. We were starting to look at context. So we can see then we're starting to enter wave three of DARPA, very early wave three, and then with promptable reasoning, still possibly very early wave three, because there's lots of shortcomings with these models, which we will explain in the next presentation. So there's a lot of information there on medical imaging models, DARPA waves of intelligence, but let's look a little bit more granularly at what we actually care about. Well, let's measure what matters here. So we fundamentally want an algorithm to most certainly provide us with low-level operations. Can it handle raw intensities well? Can it remove noise? Is it robust to contrast, different contrast and different resolution settings? Has it got the ability to reason over neighborhoods? Can it detect edges, textures, and regional shapes? Has it got the ability to have global context awareness? Does it capture long-range dependencies? Does it know whole organ views? Have we got the ability to introduce statistical modeling? Can we look at populations? Can we infuse prior information? We also want it to be able to learn hierarchical features at scale. So can we build multi-scale representations? Can it adapt to different tasks and generalize to new population data sets or new scanners? Has it got the ability to integrate information from different modalities? Can we fuse, for example, images with texts, waveforms, genetics, radiomics? And has it got that ability then for promptability? Can we, as users, prompt it to do certain things? Has it got the ability to generalize? Has it got foundational capacity? So we're very much going there from pixels to priors to patterns to prompts. And if we take each individual axis and label it with a score of 0 to 3, you might say that the most intelligent algorithm has got a score of 24. And this is all very objective, so I hope no one's overcritical. But I took 100 different algorithms throughout the different eras from 1960 to 2023. And we looked at all the different use categories. And that's far too difficult to comprehend. So then we binned each algorithm by its capability score, which was measured using the axis I've described on the previous slide. And it's obvious to see from the 1980s all the way up to 2023, we see this increase in capability of different algorithms. We see that in the 1980s, we had the rule-based top-down, so quite a low capability score. In the 1990s, we had the more structure-aware morphology and statistical priors. Interestingly,
we have 5 minutes left.
Okay. In the 2000s, we have this dip here, possibly because we've moved away from early feature engineering, and machine learning hasn't got the ability to capture global context. And then we see with the deep learning and the foundational models, we have this surge in capability there. So we want to compare some different algorithms for each wave, prior, pixels, priors, prompts, and causal. So I'll just fly through this really quickly. Let's just imagine this original X-ray, and the job of the algorithm is to identify where the healthy tissue is in the lung. A simple pixel approach will give us this result in the middle, whereas if we introduce prior information with the active contours algorithm, we see that the active contours algorithm actually just isolates the healthy tissue. And in fact, we get a 15% increase in accuracy using prior information. And this shows us how we've moved our capability score from 3 for simple thresholding to 5 for active contours, because we've got that prior information. Now we're going from feature engineering to feature engineering and shallow machine learning to end-to-end deep learning. So the task at hand here is to actually predict if a lesion is benign or malignant. There's 2 different ways we can do this: handcrafted features coupled with machine learning, or deep features that we extract using a deep neural network. And what we actually found was the deep learning performs extremely well, 82% accuracy. Interestingly, radiomics performs even better. So handcrafted features perform better in this case. But what we actually find is a hybrid approach gives us the best. So this slide is really to say that even though we can increase capability by learning hierarchical features, it doesn't necessarily mean we can increase performance on certain data types and certain problems. This is just a summary of going from a deep network, which has got local receptive field views, and using the attention mechanism. The task at hand is to segment an organ, multiple organs in the body, and we can actually see that with the UNet that's just got a local receptive field, we do quite well. But with the trans-UNet that's got the attention mechanism coupled with the features from a CNN, that actually performs the best. So the trans-UNet gives us 89% accuracy, and the UNet alone, just with the local features, gives us 86% accuracy. And the trans-UNet, then we have pattern and attention, which gives us global context. And this is an example of foundational models. We'll talk about these in the next slide. And this is just a summary here. But with the foundation models, we're taking this image and we're actually encoding information. And the patterns that we encode, we then want to learn an upsampler to give to a given task, such as image segmentation. The vision transformer actually performs a mechanism called self-attention here. So with the self-attention mechanism, we're not just looking at the local context, we're looking at global context. And this is a model called SAM, which is segment anything. And we can now take prompts that can actually also be encoded, and we can use something called cross-attention. And with cross-attention, we're looking at how these prompts are related to the images. And this allows us to build generalist models that can take as an input a bounding box and segment anything, so we can generalize across different imaging modalities. But what we actually find is this performs poorly on medical imaging data. So what we actually need to do is freeze some of the layers in SAM, and this is what MedSAM has come up with. They freeze some of the layers and then fine-tune it with medical data in order to provide us with a system that can respond well in medical image context. And here we can see the result. With SAM alone, we just get an accuracy of 68%, but with MedSAM, we get 96%. And here we have the result. SAM doesn't perform very well for segmentation, but when we fine-tune it, we can see that the segmentation is far improved from an accuracy point of view. So I've spoke about the journey from pixels to priors to patterns to prompts. And we've moved from DAPRA wave 1 all the way to early wave 3. And we can see what we can do today is high quality segmentation in narrow data cases. SAM can provide some generalist ability and a foundational capacity. And it's also got the ability to change its behavior when it's prompt or cued due to the cross attention mechanism. And we've got the emergence of vision question answer systems that may answer free-form clinical questions. But ultimately, what we need to do tomorrow is have explainability and the possibility for causal reasoning. And we need to actually infuse this a priori top-down knowledge into these large models in order to allow us to have trust and for them to be able to be used by clinicians in a very regulated field. So as David Marr once said, medical imaging is about knowing what is where and why. And if we just update that a little by seeing and understanding, which are critical points that we'll talk about in the next presentation. Thank you.
Okay, thank you, Associate Professor Dr. Rhodri, for a very interesting exposition on development of machine vision in medical imaging up to the models that we have now. So I think it's very technical, maybe more familiar to those who do research in these kind of things. So the next round is basically we go back to Prof. Micheal King. Maybe I just want to ask you, how does AI, or how are you using AI in your research nowadays? Just to continue for what you explained. So
thank you very much. Okay, so we'll continue. I'll try to be a little bit quicker this time. And let's see. So we'll share this and make it large. Try again. There we go. Okay. So this time I'm going to be talking about the application of artificial intelligence into a number of things. Dr. Smith's talk was great. His tasks and things, we'll be talking about some of that stuff. And again, keeping it related mostly to nuclear medicine. But here we're going to be concentrating on starting out by finishing up the story on attenuation correction with artificial intelligence. We'll then get into denoising, a little bit of image segmentation, talk about the need for task performance studies to validate your AI applications before they're placed in the clinic. So, and I'll move this over, okay. So attenuation correction. So why we have the CT systems out there now that are doing great. Why might we want to replace them with some artificial intelligence, the way of estimating these attenuation maps? The CTs actually do add extra dose to the patients. It's not a lot, but it's some. And if you're talking about pediatric patients, then maybe some is worrisome because they are much more sensitive to the potential harm of sort of ionizing radiation than adults. Also, CTs are definitely extra hardware cost and things that can break and you have to have repair on. So that adds expense and the need to have them. And if you're going to be doing something related to the actual emission events that are detected by your PET or SPEC system, that means that data is going to be the data that's acquired during the actual acquisition of the things that you're trying to do for the functional imaging. Whereas if you do the CT, that's something that's acquired separately. So you have simultaneous imaging versus sequential imaging, and that can give you issues where now you have to worry about the alignment of the attenuation maps with the patient and have to be constantly checking for that. And also another potential thing is that doing the sequential imaging just adds time to the whole imaging procedure. So a number of groups, many have gone out and looked at ways to estimate attenuation maps from the emission data itself, from the case of SPEC, from the photopeak and the scatter window data that you get. Kind of like going back to what we were doing at one point, I mentioned looking at trying to get it out of the images by segmenting them. Now we're throwing all the capabilities of artificial intelligence in to try and get those out. And we do the indirect method where you just try and get the attenuation map, or you could go full blown and do the attenuation map inherently into the algorithm, but you wind up with the end product being the attenuation corrected slices, and that'd be a directly a direct use of the AI methods to do your estimation or to do your attenuation correction. Okay, so give an example of some stuff that we worked on. This was to do an estimation of attenuation maps for the emission imaging, and we did an indirect approach just because we liked the idea of having that CT map there that the physicians were used to looking at and giving them confidence that we were not having some hallucination or something else that was being used to correct images with, that it was something that seemed fairly reasonable to the physicians and also for checking registration and alignment with the emission imaging. To do this work, we had a population of 1,517 list mode acquisitions that were SPECT CT studies for myocardial perfusion imaging. And the list mode part is important because in list mode, we're acquiring not the projection data itself. We're acquiring something even more, we were acquiring something even more fundamental. We keep a list of the actual events that recorded one by one. So we have their location in a head, which head, what angle was the head at, what energy was the event, what time did that event occur, are there other things coming in like R waves to relate to the beating of the heart, various other things, all kept in this list. So it's like having a copy of the patient that you can replay back the acquisition as many times as you want. By having that data, we were able to go out and define a number of different scatter windows because we set an extra big window down below the photopeak window to acquire all the scatter data. And we could then go back and look at it doing like a 4% window like we were doing for scatter corrections. People might acquire those. 10% for a different form of scatter correction, or 30%, which is what we used in the old days when we were trying to get those segmentations of the scatters windows, and use a really wide window to give us lots of counts down there. Then also, we wanted to take a look at not just how big a window you might want to use to form these maps, but also looking at what if you wanted to try and reduce the amount of time that you're acquiring the data or reduce the dose of radiation to the patient by administering less activity. So we reduced the counts in these studies by a factor of 4, and that was easy to do because we just went through and did a random number generator that we kept events on a likelihood of 1/4. So on average, we threw out 3/4 of the studies of the events and had a low count study formed. Okay, so we took 25% of this population and put it aside for testing. That left us with 905. We used 80% for training and 226 for validation. And we set this up so that during use, you'd be putting in the scatter window, whether it was a 4, a 10, or a 30%, the photopeak window, and it was the standard UNet with the encoders and decoders and skip connections. And then it would produce the attenuation maps coming out, being guided by the CT-based attenuation corrections coming in. Okay, and we went out and looked at the studies. We compared full count to quarter count, did it for 4%, 10%, 30% windows for both the full count and lower counts. And turns out that the things worked pretty well consistently across all these, so that if we acquired a wider window, yeah, things got a little bit better in terms of our precision, but it wasn't a huge amount. And if we went from full counts to low counts, yeah, things degraded a little bit in terms of precision, but it wasn't a huge amount. So they all tended to work fairly well, which was good news. And here's an example of the results. So this is for estimating the attenuation map out of a patient. Excuse me. This was a male patient, and here's the full count studies, the quarter count. We're looking at the photopeak window. Here's the 4%, 10%, and 30% scatter windows, the data from them, transverse, coronal, and sagittal views, again, for the full count study and the quarter count studies. And then we took a look at what was the attenuation map that we got out. So here's the actual measured attenuation map. And here's what we got estimated for the 4%, photopeak plus 4%, photopeak plus 10%, and photopeak plus 30% for the full dose and the lower dose. Here we throw in the heart on top of that just to help you figure out, are we doing good in keeping the positioning pretty accurate in there? And I think if you take a look at this, you can see that these studies come out looking pretty much like, all of them come out looking fairly similar. We get the bed in there, and we wind up having a pretty good comparison, except that maybe the bones show up a little bit better here than they do in these images. So we're having a little trouble with getting the bone quite accurate. But the other things are showing up fairly well. Okay, and let's see how then they occurs and we apply them. So we take those studies and we then take a look at applying them. Here's the short axis view. What do we mean by that? Well, if you take a look at the heart and think of it as kind of like a half and a little bit of a ellipsoid, so we have a ellipsoid, here's the top of it, or the base, and then we come down here to the apex. The apex of the heart is the very bottom point, and you think of this as kind of like a truncated ellipsoid with a wall inside there. If you cut, and here's the axis of the heart, if you cut the short way across it, that's called a short axis view. And that's what these are. They look like Cheerios. They should look like Cheerios that nobody's taking a bite out of. So, these all look, pretty good. This is the one with no attenuation correction, and you're getting a hint of a decrease again down in the inferior wall, and a little bit more of a decrease up in the anterior wall than you would see in these slices. Notice that this is now showing some more cooling. This is called the vertical log axis. So we take our ellipsoid like this, slice down that way through it, and you can see the anterior wall, the inferior wall, and here's the apex at the base down here. Okay, so this is with the CT, and this are estimates, and this is with no result. We also compared in these something called the polar map. What is the polar map? Well, it's kind of like you're taking the center value along all the positions in the heart wall and putting them into one picture, so you can kind of see all the slices combined into a single picture. How do we do that? Well, we start at the apex. So we take the center point apex, put it in the center. Then we go out one little ring around that. The first little ring gets a little ring in this picture. We take another step out, and we get another ring. We get another ring. So we're taking the maximums in that wall, starting at the apex and moving out towards the base. And you can see this would be the anterior wall. This is the inferior wall. And the wall towards the right ventricle, this is called the lateral wall, and except the wall, and this is called the lateral wall. This is the one towards the outside. So we can see if you take a look at the without attenuation correction, we're seeing a major dip down here, but in reality it was a small one, and we're seeing much more decreases without attenuation correction. So we brought it back somewhat. Okay, well, let's go to this next patient. Next patient, just another example, except that, on the CT, they only have one lung. This is true. Out of the 1,500 patients, we had one patient that had their lung removed. It was filled in by fibrous tissue. So there was really only one lung. And we didn't train on it, so there was no training. There was no other example of this in our training sets. But we were able to get that this patient had one lung back, well, pretty well. A little bit of a hindrance here. But, we got it back fairly well, which we thought was pretty interesting. So that was kind of neat. We were able to get that back. And similarly, we wound up in terms of, we use this to correct the emission images. Without attenuation correction, we have a major decrease down in here. And as you come across this way, well, these are between the CT and no correction, but closer to here, I'd argue, than they were there. Okay, so looks like AI can do that. How about, can we use AI to do denoising so that we can reduce either the amount of activity injected or the duration of the imaging? Yeah, and a lot of people should, for multiple modalities, the denoising is really good. we did a study with our colleagues at the Illinois Institute of Technology. Actually, they did all the DL stuff over there. We generated the images and did the basic reconstructions and worked with some of those studies to get them the data. But they did the actual turning of the cranks to do the DL denoising and optimize it. So in this one, we had 930 clinical patients. 740 we used for training and validation. We kept 190 used as the test set. And the ultimate indicator we're going to use, or the task we're trying to form, is the detection of lesions. And so we did an ROC, or receiver operating characteristic study. We used a numerical observer to detect the lesions. And the one that we used was one that's used clinically. So this is something that we actually use in our clinic. It's called the total perfusion deficit, or TPD. It's part of the QPS, or quantitative perfusion SPECT package. And it's used by our clinicians. They go through, look at all their studies, come up with what they think the answer is. Then they'll see what TPD comes up with an answer. And if it agrees with them, they're happy. If it doesn't agree with them, they'll look a little bit harder and try and figure out why there's a disagreement. So we took this as our observer, and we went out and compared filtered back projection. We optimized the cutoff frequency and the order for a Butterworth filter for low-pass filtering on that, and for OSCM with attenuation correction, scatter correction, resolution compensation. We did the same thing with the width of the Gaussian, and we optimized that to give us the best detections. So we processed a number of studies, got the best there. And then for the DL stuff, we used the 100% ones that were optimally created for either filtered back projection or OSCM as the starting point. And then we reduced the doses down to 1/2, 1/4, 1/8, 1/16, and beyond that. But using the original parameters from the 100% as the processing of these. Okay. And here's an example of what some of the images might look like. This is filtered back projection at 1/8 dose compared to the full dose. And here's filtered back projection at 1/16 dose compared to the full dose. And you can see how these are getting very noisy and so on compared to the full dose studies. Okay, so our DL was using an autoencoder. So we'd have, our encoding stages and then decoding. And we set it up so that we were extracting out of the space. We processed just around the heart itself. There's a lot of other things that are out here in the body. In our reconstructions, we just concentrated on making the heart right because we weren't looking at these other areas for clinically. So we narrowed it down to a 42 by 42 by 21 voxel size area. Our patches were 21 by 21 by 21. And we did stride of 7 voxels. Went through processing these. We used the logs function was the mean squared error. Optimizer was the atom. And Keras with TensorFlow, so on and so forth. Was used in the study. Results came out like this. That if we looked at the optimal performance, or this is the area which we took as the area under the ROC curve, AUC, area under the ROC curve, versus dose level. If we started out right here with filtered back projection, we didn't do any DL with processing there, so we took this value. As we went down to only having a half, the area went down, but it didn't go down quite as much if we did the DL processing. Went down to a quarter, it went down, didn't go down quite as much when we used the DL processing, so on and so forth, okay? When we went to doing it with OSCM, same type of thing going on, that the DL was better, but you notice it started out to be better to begin with because we had the correction for attenuation, scatter, and resolution in there, and the correction for attenuation important helped us fill in some of those false areas that appeared to be artifacts, but they were just due to the differences in attenuation. So, example of images. This is full dose studies, filtered back projection, OSCM. Notice even at the full dose, This one we see a loss of counts down here. This is a male. There was some adipose attenuation down here. It's recovered when we do reconstruction with attenuation correction. Go down to 1/16. Now this has degraded a bit. Still has the problem of artificially showing attenuation down there. The OSEM got pretty noisy at 1/16 the dose, but if we go 1/16 the dose with the DL, notice how this compares to here, this one compares to there. So the 1/16 came out looking really good compared to what we had for the full dose, whereas filtered back projection doesn't, well, it still kept the fact that it thought that there was some attenuation caused artifact in there. And we do the same thing for female, and in a female, you expect to see trouble up in here if we have female with a lot of breast tissue, and so you do. So without correction, you see it up in there and here we don't see it. You get down to the 1/16 dose with the DL processing. These are looking really good compared to that. So, okay, that's DL. That was the second one. The third one I was going to talk about is segmentation. And I wanted to see what, since now we have an AI mode in Google, I wanted to see what the AI mode in Google would do if I asked it how it thought AI was doing in terms of image segmentation and medical imaging. And if you read this, you'll see that Google's AI thing thought that AI was just great for doing artificial intelligence correct. In fact, AI thought AI was really good. So in case you wonder, that's what it thinks. So it thinks that AI is doing a great job. Okay. Again, in terms of Rhodri's great talk, he was talking about all the steps in terms of how we're doing segmentation. And we at one point we had thresholding and then zero crossings and active contours with snakes and so on and so forth. And now we're up to trying to do this with using artificial intelligence. And a big thing at the last Society of Nuclear Medicine meeting, which was the meeting I was at last week. I was there last Sunday, Monday, and Tuesday in New Orleans. The big thing was looking at segmentation methods on CT and PET and SPECT images combined to do radiation dosimetry for theranostics applications. And all the companies were talking about this and how AI has now brought segmentation into being useful in the clinic. One quick example, this is actually from the year before, but I just found a simple one to pull out, is that we now do yttrium-90 treatment for primary metastatic liver tumors. You can run a catheter up into the liver in the artery, and you put it into the artery that's going to be feeding where the metastases or tumors are, and you put in yttrium-90, which is a beta emitter, and this is put into a microsphere, a little bead, so that this thing then can block into the capillaries as you're running through there. So it gets blocked, it stays inside of the metastase, and the beta comes off and it's irradiating that. So this is a way of doing local radiation therapy without ever having to have the stuff like external beam coming through the patient's body to get there. We just put it into the parts where the tumor is to begin with, and we've selectively put it there by working a catheter up into the vessels that are feeding those lesions. Okay, but we have to find out, does it actually stay there, or how much of it goes out to the lungs? Because if you make it through the body, the blood from there comes back and goes to the lungs, and you don't want to have these things being trapped in the lungs, because then you can damage the lung. So a very important thing to quantify is the lung shunt fraction. So you do that by taking a combination of CT and SPECT. The SPECT image here is in color. The CT or grayscale is in grayscale. And you see the segmentations of the liver and lungs. And then you can use your SPECT images corrected for attenuation, as we've talked about, to get an idea of the relative counts here, where you had your vessel, where you had the artery having the tubing going into it and putting the activity in here, sticking in the spleen, as opposed to some of it maybe getting into the lung. There's a little bit of a orange hint here. And so you would take the counts here and here and compare them to the counts down there, and that would give you your lung shut fraction. And these people reported that they were able to do it much easier, and they believe more accurately with the AI-based segmentation than trying to do it by hand. That definitely took a lot longer doing it interactively, and it was not as reproducible. Okay, so we said here's some applications, but before we use them clinically, we'd really need to check them to see how well they're good at doing the task performance of studies. So there's been a couple of different organizations that have put out their thoughts on this and advocating this viewpoint. One is in terms of like
5
the
minutes.
clinical.
5 minutes. 5 minutes left.
5 minutes. I'm going to get it real quick here. This is my last slide. So we have the Society of Nuclear Medicine putting out its report in the Journal of Nuclear Medicine, advocating that we do task performance studies. And then in terms of the medical physicists, we have the AAPM task force charged to look at artificial intelligence applications. And they too put out a report. This was now a year later in 2023, saying they really need to do task-based assessment. So the idea is that clinical images are acquired for a reason. And if you want to know if the AI is working, you want to be able to test it in terms of, is it actually functioning well at solving or at giving you the answer to the reason that the study was performed in the first place. And you do that by taking the study and dividing the task. Well, for that one task we had for cardiac perfusion imaging, yeah, that was the task. We want to see how are you at picking up lesions that are there. And you have the patient population, lots of these people coming in for doing our SPECT analysis of their cardiac perfusion, image processing, so all the things we did, including use or not of DL, and then the processing to obtain that information. That would be the, in our case, the TPD, our total perfusion deficit acquisition. And then our metric ultimately was the area under the ROC curve. So you'd want to do things like that. Okay, I'm finished with this.
Okay, thanks, Prof. Mike. So I think Professor Mike King has shown some applications of AI or deep learning in medical imaging and how it can be brought to the clinical use. So I think we go back for the last segment to Associate Professor Rhodri Smith. Maybe my question is a bit cheeky. So basically the question is, we always, because I think a lot of us are researchers and we have to publish, do we always have to use deep learning in medical imaging to get published? What are your thoughts? Okay, so the floor is yours.
Yep, thank you, Ashrani. Thank you again, Professor King, for that really interesting talk. Really nice to see some of the images in nuclear medicine and the utility of AI. Very, very great to kind of come out, have some of your input on that. So I'm going to discuss two strands to the question. Do impactful papers really require deep learning and a deep learning pipeline? And in considering that question, we take a little bit of a step further as well and ask, are foundation models a threat or perhaps something that we can use with great utility in the future? So when I ask the question, has deep learning really taken over medical imaging? Because that can be...
Can you full screen your slides?
I haven't done it again, have I?
No, I can't think screen.
Sorry.
You can unshare it then.
Is that help?
I know. Go to the first slide and then.
Yeah, I'm at the first slide right now.
Present. Try to present full screen. You had it in the first.
Sorry. Slideshow.
Oh yeah. Let's see. Or you could share your full screen. Okay. No. Still not full screen.
Slideshow. Stop sharing. Share.
Sure, you did it last time, just now.
Yeah, should be that one. Share. And then go on slideshow, play from the beginning.
That's fine.
Yeah.
How was that?
Not yet. Maybe just share your whole screen, then just present.
Okay.
Yeah.
Sorry.
I'm not sure what changed just now.
Yeah, not why.
Oh yeah, good.
Is that good? Okay.
Yeah.
Sorry. We needed ChatGPT to help me with
Okay.
So yeah, I'm going to ask two questions. Do we really just need deep learning to make impactful research? And are foundation models a threat or the next tool in our kit? So there seems to be the consensus, particularly if you read the media, that AI is taking over, that computers will soon be sitting next to us, making us breakfast, taking our jobs. And let's just ask a question then, has deep learning really taken over medical image computing? So in order to do that, I did a simple PubMed search using the imaging modality keywords, for example, MRI, CT, and PET. So I was looking for original research articles from 1909 all the way up to today. And what we found was 116,000 research articles. And they have the different keywords, such as the image analysis algorithms that I previously described, the themes, and keywords that describe classical algorithms and deep learning algorithms. And what we actually see is a very steady increase in research output from the early 1900s, as one would expect. But we do very much see this exponential rise. And around probably 1990, we can say that rise starts to become a little bit more aggressive. And that's probably due to the digitization of a medical image. Medical images used to be taken by film, and only in the 80s or 90s did we start to actually digitize them. Therefore, we can start to share images more readily, perform more quantification studies, do more computing on medical images. So I think that's part of the reason why we started to see that uptick in the 1980s or 90s when it's related to research output with respect to medical imaging. But there's no doubt that as we approach probably 2020, that rise does become steeper and is almost vertical. In 2024, 2025, we see almost a vertical rise. And obviously, 2012 was the deep learning era with the advent of GPU technology. And now we've got the foundation models. So it may very well correlate with the advancements of those technologies. So when we actually look at the number of articles that are not using deep learning, but are still using the key themes that I've previously mentioned, we end up with 90,000 papers in the period 2015 to 2024. And if we look at the number that only include keywords related to deep learning, we get 25,000 papers. So from the period of 2015 to 2024, we can assume that 22% of all original research related to medical image computing was related to deep learning. So 78% of all other original research was related to other forms of image computing and other areas of study like classical machine learning or radiomics, for example. So that's a significant chunk that deep learning takes up, about 1 in 4 from 2015 to 2024. When we take that year to 2020, that should read 2024 to 2025, we actually see that we have 1 in 3 research articles are actually related to deep learning. So 34% deep learning, 66% all other. So deep learning is taking a large amount of the limelight when it comes to medical image computing, but not necessarily all the limelight. So if you look at the connectogram, and this is a connectogram based on 1,000 articles in the period of 2024 to 2025. So this is all articles related to medical image computing. So the keywords deep learning weren't specifically used. We do very much see deep learning as a theme. And deep learning pulls in classification, image segmentation, and we see lots of the cancer research, brain tumors, skin cancer, lesions, all related and tied in there with deep learning. And we probably see about 1 in 3 research articles related to deep learning. But we also see large amounts of research not related to deep learning, anomaly detection, visualization. We still even get some semantic segmentation not related to deep learning. So this shows that deep learning is very much an important part of medical image computing. And then when we look at the research without including deep learning, so specifically saying do not include deep learning articles, we still see we have large amounts of research with feature extraction, still segmentation, still machine learning, probably classical machine learning, anomaly detection, self-supervised learning, object detection. So deep learning is an increasingly important part of original research, but still not the whole. So if we do want to do impactful research, we don't necessarily need deep learning, but deep learning is undeniably a very powerful thing. It excels in certainly image segmentation and image classification for narrow data sets. So we can't ignore that. So I've spoke about deep learning quite a lot, and I just now want to cover the 2 main architectures that we kind of think of when we speak about deep learning. And that is the convolutional neural network and the vision transformer. So the convolutional neural network is a set of learnable filters that we can actually slide across the image, extracting features, and we can learn those features. And we do this in a hierarchical fashion to learn hierarchical features, and we relate these hierarchical features that we're learning to some kind of output task or output prediction. We can also, for example, have that output task to be image segmentation, so we can learn a pixel-wise upsampling. And deep learning works using the forward-backward propagation algorithm, where we feed forward to estimate the output task, then take the error function and move backwards in order to update the weights of our filters that we're actually learning from this image. And we do this in an iterative fashion in order to learn the patterns. So this is a pattern recognition algorithm that best optimize the output task. So we're very much bottom up here. We're learning patterns from data to compute a particular task. We can include a priori information if we modify this loss function, for example, and try to steer the algorithm to do certain things. But the fundamental basics of a deep learning architecture is pattern recognition and correlation. We can consider then deep learning, I think Mike has actually touched on this, in the encoder-decoder framework, where we actually take our image, we feed it into an encoder to extract the features, and we almost put those features into somewhat of a bottleneck. So these are the condensed relative parts of the information that are related to the output task. And then we can learn a decoder in order to meet the specification of our output task. So this encoder-decoder framework has been around for a very long time, and it's quite a useful way in order to kind of get an idea of what we're actually doing when we're learning these features and trying to predict output tasks. Language modeling researchers also use an encoder-decoder framework. And within their framework, they usually need to do things like predict the next word in a sentence or translate a sentence to another language. So they used an encoder-decoder framework. And when they squeeze all their information into a bottleneck, it's quite evident that if we want to predict the next word in a sentence, it's going to be very useful for us to know the words that were in previous sentences, quite a far time back in the structure of the language. So this is about how we can have context inside, when we need context inside this encoder-decoder environment. Therefore, they came up with the attention mechanism. So the attention mechanism allows each word, or each token, if you like, to be able to see previous tokens. So this attention mechanism was then applied in a vision transformer, where we split up the actual image into patches, and those patches are tokens. So now each token tries to see how important it is in relation to all other tokens. So now we're talking about having global context awareness using this attention mechanism. And if we have a vision transformer, we can then also include in a one-to-one pipeline, in a forward-backward propagation algorithm, a decoder that learns a pixel-wise upsampling and still try to perform the same task, segmented output. The key difference here, though, between a convolutional neural network and a pure vision transformer is the convolutional neural network has a small local receptive field as the filters move across. And these filters will actually respond the same irrespective of where they are within the image. So it has something called translational equivariance. So this is the inductive bias inside a convolutional neural network. The inductive bias in a vision transformer is far more loose. It's looking at global attention, and it doesn't really care about these small local patterns. And in fact, what we find is we usually need, for image segmentation, a doubling of the approach, where we actually use the properties of the convolutional neural network to extract certain features, and when we feed these features into the attention mechanism, so we have a combination of local receptive field and translational equivariance coupled with global attention. And this would be an example of something called TransUNet, which I think we see a little bit later. So we've spoke about the architectures, and we also mentioned something called a foundation model. Now, if you remember foundation models, they are models that can generalize, promptable, so we can change the behavior of the algorithm, amongst other things. So the foundation model has actually got the ability to utilize disparate data sets. So this is an example of a foundation model where we have language, such as in a radiologist report, and images. And we can feed those into encoders where we learn the patterns from the data, and we can align the image and radiologist reports within the lower dimensional domain. So this is how we can then do something called contrastive learning to relate. And this is an example of something called medclip, where we can relate images to text data by feeding them into a lower dimensional domain. We can then feed this lower dimensional domain data into something like a segment anything model, which we've previously seen. The segment anything model is a foundational model where we've learned the cross attention between box prompts and images. So then if a radiologist comes along and draws a prompt, the algorithm will automatically segment that part of the image. We can actually then use these encodings from medclip and modularize it such that we can feed it into something called SAM, the segment anything model. And as I previously mentioned, we usually need some fine tuning for medical imaging data. And this is the weakly supervised segmentation aspect of the framework. So this shows us what a foundation model is. It's a model that can actually take data from different sources, and it's trained on a large corpus of data. And then the hope is that we can apply that data to our use case for a particular task. So now we're looking at the advantages then and disadvantages of, for example, a convolutional neural network, which has a local inductive bias, and models where we have attention and foundation models. So the CNN is a narrow wave 2 model. So it performs extremely well at narrow defined tasks where we have well-behaved training data and a single task at hand. Hasn't got the ability to adapt. So the co-inductive bias is the local receptive fields, which enforces spatial locality and translational equivariance. The main disadvantages are that, the main advantages are its graded segmentation, and the disadvantages are that it can be very narrow. It's got limited global context, and it does depend on a lot of labeled data. If we take a transformer and a CNN vision transformer hybrid, these are still wave 2 with some global attention mechanisms. So we're starting to see the ability to have contextual awareness, and we can have prompts, so it's promptable in some instances, and we have that cross-attention mechanism. So the self-attention gives us this global context, and we can get long-range dependencies, so we can get understanding of multi-organ relations. The disadvantages are that it is very parameter heavy, and it lacks that locality bias if we don't couple it with the CNN architecture. The foundation models, they have the wave 2 backbone plus the emergent wave 3 behavior, because it's promptable and context aware. There's emergent wave 3 behavior in the sense that it can possibly generalize and be adaptable. There's other things about these foundation models which we'll come to talk about, which might mean they're not purely wave 3. So they're massive self or weakly supervised pre-training, and it allows us to, the prompts allow us to steer the behavior of the algorithm. The main advantages are the potential for zero-shot learning and cross-modal reasoning among text, images, and geometry. The limitations are we do need to have a lot of pre-training, and within that pre-training, there could be biases that are introduced, spurious correlations that we're not quite aware of. As Professor King pointed out and touched upon, transparency. We need to be able to trust these algorithms, and Mike is doing research on input-output, and these foundation models can be far harder to actually have that transparent opening up to see the inner workings of how they actually operate. So do we always need to have deep learning to publish? And here is just actually a deep learning, ChatGPT generated cartoon, which did take a little bit of prompting to guide it, but deep learning performs particularly poorly when you have tabular data, for one instance. And usually, I'm sure we're all aware of the analogy, if everyone has a hammer, then every problem looks like a nail. And that isn't always the case. We need to think about the problems that we're actually solving, think about the data set that we're using, and think about, do we actually need to use a huge deep learning model when other more interpretable methods are far more reasonable and far more trustworthy. So now let's take a little look at simple models, because simpler models sometimes outperform. So this task is to do with the segmentation, the prediction of survival for lymphoma patients. So we can have this PET image of a lymphoma patient, and we can see we've got lots of these lesions, and we take the features from these lesions, and we can do one of two things. As I previously mentioned, we can take the patterns that we learned from the features of the image itself and try to build a model to predict survival, or we can use handcrafted features and use those handcrafted features coupled with a classical machine learning algorithm to predict survival. And what we've actually seen in this research, the reference to this, all my references at the end of the slide, but what we actually found was simple radiomics. In this case, a simple radiomics model actually performed with an accuracy of 71% in predicting survival, whereas a deep learning model achieved only 66%. So the deep learning model in this case didn't perform as well. That isn't across the board. Lots of these things are very data dependent, but it does go to show that for certain defined problems, the most complicated solution isn't necessarily the most accurate. So simpler models can sometimes outperform. And in this example, the with the PET image, it seems to be that the baseline information is captured in simpler metrics. And the adage of Occam's razor, where the simpler model is often the best choice. The advantage, however, of this was the deep learning model does automate the segmentation process. So even if we're not using deep learning, the deep learning does very well at segmenting this task. So it isn't a clear-cut answer. Now, when we look at other challenges, for example, we get these medical imaging challenges that need to be solved. And these are tasks and competitions that people can enter. The AutoPET challenge, I think in 2023, it was a lesion segmentation challenge. Every entrance in the final challenge used deep learning. So deep learning performs very well at image segmentation. But if we look at the Hector challenge, which is predicting survival in head and neck cancer, it was literally a simple linear aggregate radiomic model with 3 parameters that outperformed deep learning models. But again, deep learning does have the advantage of automating the segmentation pipeline. Another example is the Alzheimer's prediction challenge, and it was an XGBoost decision tree that won that challenge. So it very much depends on the problems that we've got. The more complicated the algorithm, the more difficult it is for us to understand what we're actually doing. And we're all probably familiar with this term black box. With the black box, if it does something, and even if that thing is miraculous or highly accurate, we still need to know why they did that. What will we do when it fails? How do I fix its mistakes? We need explainable models in order to open up the black box to understand why, to understand, I know when you will fail, I know when you will succeed. So a simple model actually gives us clear answers, so you can actually see why a model is performing in a certain way. This is some work by Robert John at the University of Surrey, who's using convolutional networks to perform image segmentation of esophageal cancer. And we can see that the network performs very well. It segments this primary esophageal tumor. It doesn't segment this bladder, which also uptakes the radiopharmaceutical. So we can actually see that this isn't just a blob detection. We're actually detecting features that are difficult to see by the eye in the convolutional neural network. These embeddings that we actually learn, though, are a black box. And part of Rob's work is looking at explainability in convolutional neural networks. And he's actually taken the latent space, or taken all the features of the convolutional network and modeled them using unsupervised learning. And he's actually found that the embeddings within inside the deep network actually split up the lesion into different TNM stages. This is without any labeling. No one's labeled that this image has got certain TNM classifications. But on retrospective analysis, the clusters that Rob has found actually show that he's been able to disentangle the information that's encoded in the deep network. So the outcome is that we have a latent access which becomes clinically interpretable, and we're able to have these features then that could be used by the radiologists or the clinicians to understand what the network is doing. So we have explainability. So we have explainable features, and there's quite a lot of research out now that shows that if we have explainability in these networks, we actually end up learning better features. So in order to have an explainable model, we actually need to be able to have transparency. So we need to open up the black box. We need to have transparent models. So we need to be able to show the layers of the models, the inputs and the activations. We also need to have this level of explainability, show what the model is doing and when, show how it responds to outliers. And when we have explainability infused into these models, we can start to also inject prior knowledge like physics anatomy, clinical intuition, and top-down knowledge to try to steer the learning in a particular direction in order to disentangle the activations of a network such that we can do things like causality analysis and counterfactual reasoning. Because we all know that correlation doesn't equal causation. So by making a model more explainable, by injecting prior information, we can actually move to having models that have causation as their primary driver rather than bottom-up pattern recognition and correlation. And only when we have causality can we actually start to trust these models. And the causality might even anchor the generalizations of the models so we avoid spurious correlations. And with that, we can then start to work towards having advisable systems with a human in the loop that allows us to actually interact with the AI in order to help it guide us and us guide it. So are foundation models a threat? I would argue that for simple problems where we need efficient, transparent solutions, we're always better off sticking with something that we can understand and sticking with Occam's razor. It's usually the faster of the car that will get us over the line. But for more advanced research, I think that we need to accept that deep learning is going to be part of the corpus from here on in, and we can work on the modeler aspects of infusing transparency, infusing explainability, prior knowledge, and causality into deep learning and large language models in order to have systems that we can trust, that will also breach regulatory hurdles, and that we can use in the future to perform the key tasks I previously mentioned, improving diagnosis, quantification, for the ultimate goal to increase the patient experience and personalized therapy. Thank you.
Okay, thank you, Dr. Rhodri Smith. I think that's a nice way to close the final question. So it's not just a matter of using the model, it's basically how to use it and how to explain the results. So I think all of you, the audience, have heard from both of them for the past almost around 2 hours. We're a bit early time, so we have more time for questions. So the floor is open for any questions. So you may, I think you can just ask directly. So anyone? Or maybe if there's something to understand. With online talks. Maybe everyone understands. Or maybe I'll start first with my own question for both speakers. So anyone else in the audience is welcome. So my question is maybe not directly related to the topic of the forum. Basically, how both of you, start a project with clinicians, because I think that's one of them, myself, maybe some others, the major hurdle. So, does the project have to start from the technical researcher or from the clinician? Maybe, because I think Prof. Mike has shown quite example good project between himself and University of Illinois Technology. So either one of you, how to start basically a medical imaging research project for today?
Well, I can make a comment somewhat that I have an advantage in that regard of working with the clinicians, because I truly do. My office is along the hallway with theirs. And I am the medical physicist, the clinical medical physicist within the Division of Nuclear Medicine and the Department of Radiology. So I help them in the clinic with their issues, and they in turn, are very willing to help us. And historically, a lot of the things we worked on came out of the clinic in terms of seeing problems or things that they had. So whether the topics we worked on research-wise were initiated by the physics, but maybe we initiated the writing it, but the actual problems were ones that they pointed to us as needing to be addressed.
Okay, thanks. Dr. Rhodri Smith, any thoughts?
Yeah, I agree with that. I think with lots of these things, the problems that are usually foundational and static. So I think some of the key themes that I've pointed to, like image enhancement, image processing, image quantification, interpretability, and research, as we've seen, is exponentially growing, and a lot of these problems are not actually solved. We have solutions to them that are acceptable for this day's research, but that doesn't mean that we're at the end of the road there. So when a clinician is even using perhaps a system that provides decent quantification, but then we might read the research that shows that a different system might actually be more beneficial. It's quite easy to get them on board with that respect. So when they're engaged with wanting to perform at a greater intellectual level for their patients as well, so they have better outcomes, it's usually quite easy to get them on board to use state-of-the-art technology. So I see part of the role as a medical physicist to infuse that state-of-the-art technology back into the clinical domain. So yeah, I think is just for the patient benefit as well, so everyone's on the same page.
Okay. Good comment. So any questions?
Hello, I'm Hanani from. Hello, I'm Hanani from Radiology Department. I'm physicist. Okay, so my question is there any possibility for me to do like a research attachment at your university? Because previously I'm working with a brain tumor patient, and then we just started to do the radio mix. Yeah, actually really just started. We just try to apply a grant, but still no success. Yeah, do you think is there any possibility for me to do a research attachment at your place? I am a researcher, physicist researcher. Yeah.
Yeah. Question for you. Are you working in what modality? Because I only can answer.
I'm working with functional MRI, but also MRI.
Yeah, well, I mean, we have other people who are working in MRI here, and I can't speak for them. But if you send me your interest and things like that, I can forward it, and so there's that possibility. But I can't speak for them. I would also mention that things are a little harder now than they were a few months ago. I'll leave it at that.
Okay.
Because monetary funding, all sorts of issues research-wise are in a greater state of flux currently in the U.S. than they have been for many years. I'll put it that way.
Okay, but I will send the detail and CV to you. Yeah. And yes.
Well, please do. I have a couple of people I can send it to. But I can't guarantee their response. I can guarantee that they would have responded before early 2025. I'll put it that way.
Okay, thank you. How about you, Dr. Rhodri? Do you have?
Yeah, similarly, so my main area of focus is nuclear medicine and PET, but I've got some colleagues here in the U of A biomedical engineering department that are always increasingly interested in collaboration and attachments. So if you send me your details, I can make sure that gets past the right person. And I've only actually been here for about 6 months, but I am aware that we do have lots of international collaborations and lots of people coming and doing great work. So absolutely send me your details through.
Okay, thank you very much. Thank you.
Okay, thanks. Any other questions? I'm not sure if everyone understood or maybe thinking of the questions.
It's great to know we did such a good job that there's no other questions.
Could be either way. I'm not sure.
Yeah, or the other way.
So still have some time.
Hello, hi, speakers. My name is Shaira. Sorry, I couldn't open my on my camera, but I have a question. Since I'm coming from a background that's not related to any medical or imaging at all, so what is your comment? I mean, this is a question to both speakers and also the moderator, if you can answer this. What is your comment for those who are interested to delve into the imaging research, because they start to see the needs of combining this field with, for example, on what I'm working on right now on the microbiome. And since I do not have any background and based on the papers that I've seen, usually I'm thinking of going to the open software to do the analysis of the data. Any comment on that?
So,
is my question clear, or?
So you're working in microbiome? Am I correct?
Yeah, like microbiome and gut axis is kind of related. Nowadays, people are going into, trying to see if there's any issue with gut microbiome, and these affect, like the brain function and everything. So since I'm never been doing anything with the brain, so I'm thinking of, start delving into that kind of research. But given that I have no background, and from the reading, I might be inviting some of the people from the medical physics, but yeah, maybe your comment on those who are interested to start working with this kind of field. Yeah, thank you.
My thought is perhaps that your interest might be more preclinical imaging oriented than clinical. That means working with mouse or rat or even pig or dog or whatever models where you can have exact control over the biome and so on and so forth. And you should know that there's a lot of very nice imaging systems out there that are tailored for imaging those research models, scaled to the size and to meet all that. We have a good group at UMass that's doing a lot of research in that way. If you send something, I can try and get it to their hands. It might be too big of a jump to try and work with somebody in the clinic at your stage yet, but the other things are there's very good things going on.
Any thoughts, Rhodri?
Yeah, I think I agree with Mike. I think what you're probably actually looking for, though, is more of a collaboration. Yeah, it sounds that you've got your foundational field in your subject matter, and I think having an appreciation for medical imaging and how you can tie those details in. But together, our initial tie-in and foot in the door is probably to try to build some kind of collaboration with a preclinical team somewhere. So that would probably involve even just doing some kind of scope and literature review, finding out how imaging can actually tie in with your work, and then probably targeting more local imaging experts in your area to see if you can win some kind of small grant to extend those ideas. And then from there, you can actually then take bigger strides into medical imaging yourself, if that is your interest, and then try to become a subject matter expert in the imaging domain, if that's how you feel you want things to go. So I think just probably a little bit more foundation work and trying to build collaborations.
Okay, nice advice. Any more questions?
Hello.
There's someone. Can you introduce yourself and this?
Yeah. Good morning. My name is Adam. I'm currently working on medical imaging, so to speak. I had some experience working with cone beam computed tomography. I would like to ask a few questions. Just one, actually. in the advancement of artificial intelligence, as what we have deep learning and so on, is the conventional or the traditional way of processing medical images, still relevant in a let's say, for example, if you were to use AI-based algorithms, but instead we use all those traditional, very hard-coded image processing algorithms as benchmarks. I'm not sure whether is the question clear enough or not, because when I did my research, I was doing all those very analytical based image processing algorithms, and suddenly AI just pops up from I don't know, all out of a sudden, and it feels a bit backwards. So I'm just wondering, because I'm still in the process of trying to embrace this AI advancement, but where do I put all those other already developed, all those old school, I guess, antique medical imaging algorithms? Thank you very much.
Okay. So I was
going to say, as an antique myself, I would say that they are still, I think from Rhodri's talk, he was showing that AI has not quite got the majority of it yet, but it's working on going there. So there's still a lot that can be done without AI. That doesn't mean that you should try and avoid it. If it makes sense to use it, you should definitely go there. But yeah, you can definitely do a lot of things without AI. And understanding those methods can help you understand and explain, at least this is my belief, what comes out of AI.
What about Rhodri?
Yeah, Adam, I think that we've actually met, so nice to hear from you. My advice would be, and I think you probably touched on this on your question, you've built analytical methods and models. Firstly, if they were fundamental and state-of-the-art, they can serve as a benchmark. Secondly, AI, in what I see its current form, is very much a very strong correlation driver. The physics models and analytical models exist for a reason, in that we were able to describe analytically how something can perform, and it does very well, and avoid spurious correlations. So we don't really understand yet how those spurious correlations can feed into AI systems. So the analytical methods you've got are very much part of the, what I would say, a priori state where you can actually infuse those models into more pattern recognition algorithms. So you can have physics-informed models. Now, if we can come up with an equation or an analytical way in which we can describe a system and it performed well, that doesn't mean that it's now worthless because we've got a pattern recognition algorithm. In fact, it could be more worthwhile because you are possibly narrowing down the scope of the number of parameters that you need to use in a more advanced algorithm. So then you're going to get speed increases, you're going to get explainability. You could then start to look at causality and input-output. So I think that you're in a good position and a good spot, and I don't think that you should just throw everything away. I think you should more certainly try to look to infuse and modularize and latch on, and I'm sure you'll get up to speed quite quickly.
Okay, thanks, Dr. Rhodri Smith. So any last question? Or I guess we close the forum. Okay, maybe everyone understood. So